left ventricle. Okay? Now, does everyone see these little strings attached to the valve? And do you see where they're anchored to the wall of the ventricle? Does everyone see that? Everyone see these strings and how they're anchored to the wall of the ventricle? Those strings are called chordae tendineae, and where they're anchored is called papillary muscles. What's the function of those? Well, once the blood completely fills the left ventricle, then the ventricles have to contract. And when the ventricles contract, they want to push blood up and out through the top of the heart, through the base of the heart. So they have to be able to pump blood and go against gravity. Does that make sense? Because they're wanting to pump blood up and out through the top of the heart. So they have to provide enough force to beat gravity. Does that make sense? All right. Well, what's to stop the blood from just going back up into the left atrium, right? If it was just an open hole, blood would just go back up into not all the blood would be directed through the aorta, but some of it would go back up into the atrium. That's not very efficient. So those valves, okay, they're anchored by those chordae tendineae being anchored by those papillary muscles to the ventricular wall. So when the ventricles contract and there's all this force, the papillary muscles also contract, tugging on those chordae tendineae and keeping the valve shut, all right? So that the valve doesn't prolapse up into the atria. Does that make sense? Okay, so that's the function of the chordae tendineae and the papillary muscles, is that when those ventricles contract, it tugs on it, keeping the valve closed so that blood only has one option of going up through the aorta, and it can't go back into the atrium. Does that make sense? Okay, so the left ventricle is going to contract. The left ventricle contracts, provides a great enough force to push blood up and out through what's called the aortic semilunar valve. It's all, which you can't see on the cow heart, but you can identify this aortic semilunar valve on the models, okay? So if we follow my finger up and out, not through this, because that's the bicuspid valve, it's gonna go this direction. And then look, that's the aorta, okay? I'll do that again. Okay, so here's the left ventricle. It's not gonna go back up this way. This is the bicuspid valve. It's gonna go up this way through the aorta. Okay, through the aortic semilunar valve and then through the aorta. Okay, does everyone see? So not back through this way. This is the bicuspid valve. That leads back into the atrium. It's gonna go up and out through this aortic semilunar valve through the aorta. Does everyone see that? Okay. All right. So ventricles contract, pushing blood up and out through the aortic semilunar valve through the aorta. Okay. From the aorta, the blood is going to be directed through arteries, then arterioles, and then capillaries. What happens at capillaries? Does anyone know?
Gas exchange.
Gas exchange. Fantastic. So capillaries are a site of gas exchange. Tell me about the directions of those two gases. Where's oxygen going to go?
Into the vessel.
Into the
muscle.
Into the tissues. Yeah, whatever tissue that capillary bed is supplying, right? So oxygen is going to go from the blood into the tissues, correct? Because those tissues need more oxygen to carry out more cellular respiration. Well, those cells have been carrying out cellular respiration and building up lots of what? CO2 as a waste byproduct. Where is CO2 going to go?
Into the blood.
Yes, from the tissues into the blood. So now we have this blood that is high in CO2, low in oxygen. Deoxygenated blood. Yes? What do we need to do with that deoxygenated blood?
Get it out, or get it back to the lungs.
Get it back to the lungs so that we can do what? Carry out gas exchange again and get more oxygen and dump off all that CO2 to be exhaled. Well, it's traveled a really far distance. So now the blood it's lost a lot of its pressure, right? So we actually have to get the blood back to the heart so that the heart can pump again, giving it a little more pressure to get to the lungs. Does that make sense? All right. So now I'm gonna have to turn the heart over to the posterior side, okay? And if we're dealing with deoxygenated blood from below the heart, it's going to enter into the right atrium through the inferior vena cava, which is right here, okay? Inferior vena cava. If we're dealing with deoxygenated blood from above the heart, it's going to enter the right atrium through the superior vena cava, which is right here. And look, if I put through the superior vena cava, what am I pumping? This is the right atrium. Here's the inferior vena cava, If I put my finger in, what am I pumping? The right atrium. Does that make sense? Okay, so superior vena cava, bringing deoxygenated blood from above the heart back to the heart, back to the right atrium. Deoxygenated blood from below the heart enters through the inferior vena cava. Does everyone see how this one is more above, this one is more below? Superior, inferior, okay? Heads to the right atrium. Now, I mentioned earlier in class that there's a coronary circuit, like a coronary circulation. That's dealing with the vessels that actually provide the heart tissues themselves with blood, okay? Now, that blood, all that oxygen in that blood is gonna get used up by all of the heart cells, the cells of the heart, right? And the cells of the heart will produce CO2. So deoxygenated blood from the heart itself will actually enter through the right atrium through what's called the coronary sinus, which is a very enlarged vein, okay? And that coronary sinus also dumps into the right atrium. Does that make sense? Okay, so what happens after the deoxygenated blood fills the right atrium? The atria are going to contract, right? And it's going to push blood, okay, deoxygenated blood down through what's called the tricuspid valve. So this is the right ventricle, and look inside. Does everyone see that flap up at the top of the right ventricle? Does everyone see that? This valve all the way up at the top? Does everyone see that? Does everyone see that flap all the way at the top of the right ventricle? All the way up there? See it? Did you see it? Okay, all right. It's a little hard to get to because it's such a small area, okay? That valve is separating the right atrium from the right ventricle. So the atria contract and blood's gonna be pushed down through the tricuspid valve, which is also an atrioventricular valve, but it's the specific one between the right atria and the right ventricle. Does everyone follow? And if you look, you'll also see what? Chordae tendineae and papillary muscles. Chordae tendineae anchored to papillary muscles, right? Because of the same thing. When the ventricles contract and it provides that force to push blood up and out, we don't want that blood from the right ventricle to go back into the right atrium. We want it to be directed through the pulmonary trunk, okay, only. Does that make sense? Okay, so all that blood goes through the tricuspid valve, enters into the right ventricle. The ventricles contract, pushing the blood up and out through, and actually it's kind of hard to do on, but let's see, that goes to the, I think there is a heart that I can do this with. No, okay. There's another heart in this classroom where you can actually go from the right ventricle and put your finger and it goes up through the pulmonary trunk. So if you want to like prove to yourself, one of the hearts in the room does that. But when the right ventricle contracts, it pushes blood up and out through what's called the pulmonary semilunar valve, okay, which you can't see on the cow heart, but you can see on the model, through the pulmonary semilunar valve, through the pulmonary trunk, which is this vessel right here. That one that I told you how to identify the anterior, okay? This is the pulmonary trunk or the pulmonary artery, okay? This is an example of an artery that's carrying what? Deoxygenated blood from the right side of the heart. This pulmonary artery is gonna lead to where? It's gonna branch off into other pulmonary arteries that are gonna go and enter into the lungs, right? Eventually getting to those pulmonary capillaries, and what's gonna take place? Gas exchange. Oxygen is going, that oxygen that we just inhaled will diffuse into the pulmonary capillary blood. CO2 is going to diffuse from the pulmonary capillary blood into the lungs to be exhaled. Now we have oxygenated blood. Where does it have to go? To the heart. Through what? Pulmonary veins. Those pulmonary veins dump that oxygenated blood into where? The left atrium. Then the atria contract, pushes blood down through the bicuspid valve into the left ventricle. And I've already done all the, so I did one big circle and I talked about these circuits separately, but remember that the same time that both atria contract together, both ventricles contract together, both circuits are happening at the same time. Does that make sense? Okay, any questions? No?
Why are they called semilunar?
Semilunar because they have a half moon shape to them.
Okay.
Yeah.
But it's the same thing when they're not listed as semilunar. It's just the valves,
they're a slightly different shape. It's just the semilunar has like they said it looked like a half moon shape, so semilunar half moon shape. But and then the atrioventricular valves don't have that same shape, but the overall function is the same, right? So the point of valves is to provide a unidirectional flow of blood. Okay, those semilunar valves, the aortic semilunar valve, the pulmonary semilunar valve, what happens to them is as blood gets pumped through, let's talk about the aortic semilunar valve, okay? The left ventricle contracts, pushes blood up through the aortic semilunar valve into the aorta. Well, as soon as blood starts to fall back on the aortic semilunar valve, because of the structure of that valve, it actually closes and prevents blood from going back into the left ventricle. So the shape is required so that when blood falls back, it actually closes it. It's the pressure in that aorta which closes the aortic semilunar valve, preventing blood from backflow. Does that make sense? So all valves have the same overall function, to prevent backflow and to ensure a unidirectional flow of blood, which makes it more efficient. Because if you just had blood just going through the aorta, back into the atrium, it's not very efficient. So unidirectional flow of blood and prevents backflow. That's what valves do.
And isn't the sound, like the lub-dub sound, is the sound
actually,
of the valves opening and closing?
Yeah, so when you listen to a heartbeat, that lub-dub is actually those valves closing. So the first sound, the first heart sound, are the atrioventricular valves closing. The second sound would be those semilunar valves closing. And that makes sense, right? Because the atria contract first, so those atrioventricular valves would close first. Then the ventricles contract, and so the semilunar valves would close second. Does that make sense? All right. Any other questions?